This is Unit 5B, Part 2. It's the homework from last night. Okay, what is a sampling distribution? So again, today's Unit B is really just introducing this idea of sampling distribution. And with that, there are such a thing as biased and unbiased estimators. We're trying to, again, the sample, we're trying to estimate the parameter, right, about the population. So usually the mean or the proportion. That's typically the most common ones, but sometimes we do other things. So statistic can estimate the parameter. Again, that's what we're doing. But it's an unbiased estimator if the mean of the sampling distribution is equal to the value of the parameter being estimated. So if that's true, we actually did an example in the last lesson where we saw that the mean of those four heights which is the population parameter there, was equal to the sampling distribution mean. If you average those, that mean was the same. The mean of the sampling distribution is also known as the expected value of the estimator. So we could use that name. I'm not sure how often you use that, but we could. So here's a simulated sampling for a population maximum value. So maximum, instead of mean or proportions, this one's measuring the maximum. So is that the same, I guess? So is that an unbiased estimator, I guess? So if the mean of the sampling distribution is equal to the parameter being estimated. So the mean of the sampling distribution, so I don't know what the mean of that data is, but I know it's not 100. 100 is the maximum. The mean is probably between 80 and 100 there. I don't know, 85 maybe. I'm just taking a guess there what the mean might be, but it's definitely not 100. Clearly not. When you look at the distribution, the mean, around 85-ish, will not be equal to the parameter, in this case, the maximum value of the population. So we created, remember we did this, we did the sampling distribution. Is the sampling range an unbiased estimator? Oh, well, we didn't do the range, or we just kind of mentioned the range maybe, but we didn't really do it. So here's the dot plot of the range. So, well, you'd have to get your calculator out at this point, right? So if you want to see what the expected value or the average or the mean of those values are, of those range values, so you do 1 plus 3, there's 2 3s, there's 2 4s, and 1 7. And we're going to divide by 1, 2, 3, 4, 5, 6, divide by 6, we get 3.666, right? So is that equal to the mean of the population is what it's saying. Let's see. So is the sample range an unbiased estimator of the population range? What's the range of the population? The range of the population would be 75 minus 68, which is 7. Well, 7 is not equal to, 7 is not equal to 3.666. So I would say this is not an unbiased estimator here. Yeah, so and range doesn't usually work like that, right? So that's what it is. Because the mean of the sampling distribution of the sample range. So when we took the sampling distribution range, it was about 3.66. That's not equal to the actual range of the population, which is 7. So sample range is not an unbiased estimator of the population range. That's true. Actually, when you take a sample, usually the range will be smaller. That's almost always true. It can't be bigger, right? So that's not even really possible. What is the difference in the sampling distribution of the mean year penny when it was taking 5 samples compared to 20? We're going to actually do this activity at some point here. This is what it looks like for the penny data for one example of selecting 5 pennies. And for everybody, maybe a bunch of students in the class did that, and they came up with all this data. And sample mean year of the penny n equals 20. So I like side by side. I almost wish they were kind of vertical from each other rather than horizontal. It might be more obvious. But actually, let me see if I can do that. Okay, so let's look at this vertically. I think it just might make more logical sense to your brain to see the range a little bit easier. So it looks like the lowest year, so when you took a sample size 5, each one of those X bar means you grab 5 pennies, you average the year that are representing those 5 pennies, and you plot it on the graph. Looks like the lowest average is somewhere around 1993, and the highest average is somewhere around 2019. So that's when you grab 5 pennies at a time and find their average. Now, if you grab more, like 20, wow, that's a lot more. Look how the graph changed. So it did vary all the way from 1993 to about 2019. Now the lowest it goes is late 1900s, 1998-ish or something. And the highest it goes is 2013 instead of 2019. So quite a bit less variation here. It looks to be a better indicator. So you're guessing with both of them. You're guessing the be able to do the 2008. Somewhere around 2008 is the mean for both of them, but it's a little bit more obvious with the 20 data there because you can tell it's taller. It's not quite looking normal, but it's maybe more symmetric than the n equals 5 was. So, but definitely the variation is one of the biggest things there. You can see the variation is a lot smaller. As the n value increase, you're going to get a more accurate, more precise prediction here. So let's see what we've got. The sampling distribution with the larger sample size has much less variability, right? Much less of a spread or variability there of the data. That's true. So decreasing sampling variability will have less variability when the sample size is larger. So if we want less variability, which is good, we have to do a larger sample size. So a larger sample size always helps our data to be better. For quality control purposes, supervisors at a battery factory regularly select random samples of batteries to estimate the mean lifetime of batteries they produce. Here's a simulated sampling distribution, X bar, of the sample mean lifetime in hours for 1,000 random samples of size n equals 100 from a population of AAA batteries. Okay, so simulated mean lifetime. There's again, that's for sample size of n equals 100. What would happen to the sampling distribution if the sample size were changed to, instead of n equals 100, n equals 50? So what's going to happen? It's going to have more variation, less variation. Well, n equals 50 is not as good. It's going to have more variation there. Simply will be much more variable than the sample size because the sample size is smaller. I didn't show a picture, but it would definitely look different. We're talking about the same thing. If here, how will this change the sample size, affect the estimate? So that's interesting. So would the estimate change much? It's not going to change much, but it's just a little bit more precise or easier to see the results when you have a larger sample size. So the means of both of them should be pretty close, but just not quite as precise and obvious. Changing the sample size affects the variability for sure, but not bias. As long as the sample is randomly selected, sample mean will be an unbiased estimator of the population mean, no matter the sample size. Okay. So bias, if you think of this as like an analogy of, aiming an arrow at a target, bias means our aim is off. You're going to miss the bullseye in the same direction. we're trying to hit the population parameter. That's our goal by taking the statistic or taking a sample and finding the statistic there. But bias means you're not even aiming correctly. Whereas high variability, which is caused by having a small sample size oftentimes, means that repeated shots are widely scattered on the target. In other words, we're not going to get similar results a lot with that. So if you had again, back to the arrow analogy, if you had high bias, so you're not aiming correctly, but low variability means all those shots are kind of all in one cluster there, but it's not hitting the bullseye. Low bias means, when you don't have a lot of bias, you are almost hitting the bullseye, or at least like you should be, in this case, centered around the bullseye. But the variability is so much that you're not actually hitting the bullseye very much. High bias means you're not aiming at the target. High variability means they're all spread out. Ooh, this is terrible. This would be the best, right? No or little bias and very low variability, so they're all clumped in the center. We can try to use the word more precise than accurate here when you're talking about the sample size increase. You get more precise estimates. We shy away from using the word accurate there, even though students love to use the word accurate in that setting. It's English-wise, it may be okay, but stats-wise, we prefer precise here. Okay, you're done with the lesson. Just look at a couple examples. Remember, we talked about the electoral votes, I think, the other day, or at least we might have. Sort of 3 states that have at least 15. This is called the sampling distribution of the data. So, in this case, the delegate data. Sample proportion with at least 15 electoral votes. So is this an unbiased estimator? I don't know. Let's get our calculator out, right? So you would add up all those values. So I'm going to, instead of typing 1/3 3 times, I'm going to say 3 times 1/3 plus 1, 2, 3, 4, 6 times 2/3 plus 1 is 6. Now there's total of 1, 2, 3, 4, 5, 6, 7, 8, 10. So divide by 10. So the typical or the mean of the sampling distribution here would be 0.6. And if you look at the question, 3 of the 5 states have at least 15 electoral votes, so 3 divided by 5 is also 0.6. So that is an unbiased estimator. That's good because it does match the population proportion in this case. So the owner of a greenhouse grows thousands of roses. Aphids are small insects that severely damage roses and owner's profits. The greenhouse employees take random samples of 40 plants 3 times a day to check for aphids. If this is a simulated sampling distribution of p-hat, is what that is, sample proportion of plants for 1,000 samples with sample size n equals 40. So it's a lot of them, but the sample size is n equals 40. What would happen if the sample size were 120? Well, it's going to have less variation. That's the big concept there. Probably look a little bit more symmetric and maybe more normal, that kind of thing. How will this change in sample size affect the estimate? The estimate should be pretty close, either way, actually. So 0.1075 or something there. I'm not sure what that is. Cutting half exactly, but something like that. They're going to have a very similar value. It'll be very, very close to each other. It's a little bit more precise when you have a larger sample size, but not that big of a difference there, really. That's your lesson for today.